Let's begin. Today is one of those days where your attendance is really going to count. It's going to have an outsized weight. All of your November attendance is going to depend on today. So let's see. If you're out there, let your friends know if they're not here today, they're not going to get their attendance for the month. Okay. For the next 4 lectures, we're going to be talking about neural networks as generative models. And this lecture and the next is going to be all about variational autoencoders. Now, so the problem question we're asking ourselves is this. You have a collection of pictures, maybe landscapes of this kind, and you want to train a neural network model that can learn from all of these landscape pictures and then not classify them, not make predictions about them, but to actually paint a new landscape of its own. So you want the neural network to generate new samples of the kind of data that you've actually trained it from. So again, we've seen neural networks can classify, they can perform regression, but now what we really want to see is whether neural networks can be trained as generative models where they can generate newer data of the kind that they've seen, where the data can be arbitrarily complex, like paintings of landscapes. So, but before we even get there, the question is, what is a generative model, and what are the various things we need to know about generative models? So in today's class, magically enough, I'm not going to be talking about neural networks. In fact, I'm not even going to be talking about anything nonlinear. That is being punted on for the next week. So here's what we're going to be talking about. What are generative models? How to estimate them, and we're going to be talking about the problem of the expectation maximization technique. How many of you have heard of expectation maximization? Some of you have. So how many of you are prepared to come up here and explain it to class? Raise your hands if you are. Okay, no volunteers. I'll do it for you. Now, what's a generative model? It's a model for the probability distribution of any given data x. Now, by the way, there are a lot more slides. There are 156 slides in the deck. We're only going to cover about 60 of them in class. But I would like you to go over the rest of the slides. Some of it is animated, but it sort of explains many of the concepts behind what we're talking about. So from a computational perspective, a generative model is this magic black box where you feed it some random input, and in response to the random output, it generates data of the kind that you really want it to generate. For example, you'll be feeding this model which has been trained on landscapes a random input, it should generate a new landscape. This is a statistical problem. So here is how it's normally stated. You're given some observed data, x. In the example I just posted, those would be the landscapes. And you're going to choose some model, p of x semicolon theta. That would be a neural network if that's how we're modeling it. But for today, these are not neural networks. And this is a parametric model. It has some parameters theta, and for any particular set of parameters, it's going to represent some probability distribution function. And our job is to try to estimate these parameters given training samples from the data. So to give you some idea, give you an example, let's say you have dice and you rolled it a whole number of times and you got this histogram of outcomes. Now the multinomial distribution is a generative model. The act of giving it a random input is the act of rolling the dice. It's going to give you an output. Now this multinomial distribution can have different forms. So here's a question. I rolled my dice. I got this histogram of outcomes. And then I'm asking you to choose which of these 2 distributions represents the dice. So who is number 22? Which of those 2 would you choose?
The green one, because it has like the 2 humps.
Why?
Because it has like the 2 humps at 2 and 4.
It matches the shape, right? So, or something else. This is actual data that I got from some speech recordings. if you actually grab some of the features that we've given you for homework 1, 2, 3, 1 and 3, and plot a histogram, you're likely to get a histogram such as this one. Now, here are 3 different badly drawn Gaussians. And one of those Gaussians represents the distribution or the generative model that could have generated this data. So if I were to ask 21, who's 21, which of these 3 Gaussians you would choose, which one would you choose? The red one. Again, why? Pardon me? It kind of matches the distribution, right? So now, what do I mean by matching the distribution? Basically, you're saying that this sort of matches this shape. You're saying over here again, this guy matches the shape that you see over here. That's a very subjective way of describing things. What is an objective way of describing it? So objectively, this one is assigning lower probability to events that are less frequent and higher probability to events that are more frequent. In other words, this data looks like the kind of data that this distribution could generate under normal circumstances, right? And so the assumption we'll be making over here is that these data are generated by draws from the distribution. So the generating process draws data from the distribution, and the assumption we made, the assumption you guys made when you chose the specific distributions that you did choose, was that the world is a very boring place. So the underlying principle behind a lot of statistics is that the world is a boring place. It really is, in a statistical sense. The odds that you have seen something unusual are very low. So the assumption we are making over here is that whatever data we did observe are kind of typical for the distribution that you saw. So given a collection of distributions that you could choose from, you are going to choose the distribution for which the data that you observed are most typical. Mathematically speaking, you are going to choose the distribution which has the highest probability of having generated the data that you just observed. So this is the so-called maximum likelihood principle, which is also alternately the world as a boring place principle. So let's look at a couple of examples. One was the histograms. The other was the histogram of the roll of dice. The other was a histogram of real numbers. The one on top is a it's a category distribution. The output can be one of 6 values. The one at the bottom can be modeled by a Gaussian distribution. So I have a collection of data points. And if I have a collection of data points, the principle I'm using is I'm going to choose the distribution which has the highest probability of having generated these data. So which means first I have to characterize the probability. So this is what I will do. If I have a lot of data, do we have a chalk? So if I have a collection of data which is x1, x2, these are all my training, all of the data that I have observed, then the probability of the data that I've observed is just going to be the product of the individual probabilities, assuming they're all independent draws. So that's basically what we're saying out here. And so when you have the category distribution, the probability of the data that you see is going to be the product of all of the observation over all of the observations of the probability assigned to the observation. The same thing in this case as well. And in the case of the category distribution, we want to choose the probabilities for the various outcomes, the 6 sides of the die, such that this probability is maximized. Or alternately, instead of the probability, you can take the log of the probability, because the log is a monotonic function. But the log is a nice thing because it converts multiplies to summations. And so you could be choosing the probabilities for the faces of the die that maximize the log probability of your observations. Or alternately, in the Gaussian case, the parameters of the Gaussian are the mean and the variance. You would be choosing the mean and the variance such that the log probability of the collection of observations is maximized. Straightforward, nothing particularly fancy, but this is just the world is a boring place principle applied again and again, right? And so if I work through the math, in the category distribution case, I can group these outcomes by value. So I have, say, some n1 instances of 1, some n2 instances of 2, and so on. And so I can just group them by the number of times each outcome happens. In the Gaussian distribution, this term p of x, of course, is Gaussian. So now writing it differently, you're saying that in the category distribution problem, the total probability of the observations you got is the probability of 1 raised to the number of times 1 was observed times the probability of 2 raised to the number of times 2 was observed, and so on. And here, of course, in the second case, these are all just probabilities of Gaussians. And the log of a product of probabilities can be converted to the sum of the log probabilities. So you're going to say that you want to choose the probabilities for the faces of the die such that the sum over all possible outcomes of ni, which is the number of times that our outcome was observed, times the log of the probability of the outcome is maximized. Or in the case of the Gaussian, you're going to choose the mean and the variance such that the sum over all observations of the log Gaussian is maximized. Now, I'm not going to go work through the details of, obviously. The idea here is, this is just, we're sort of presenting how we approach this problem. And if you actually work through the arithmetic, you're going to end up with a very familiar solution. That your estimate for the probability of any outcome is the fraction of times that outcome was observed. So the estimate for the probability of 1 is the number of times 1 was observed divided by the total number of trials. Or the estimate for the mean and the variance of the Gaussian are simply your standard formulae for mean and variance. These just end up being maximum likelihood estimates. So nothing particularly complicated so far. It's all just counting. Any questions? No. Okay. So there should be no questions. You published the poll? Yeah, Jay did. Yeah. Can you time it? We are getting to, well, there are 100 people watching. That's a good thing. Okay, 5 seconds, guys. All right. So again, to restate this, the maximum likelihood estimation principle literally states that the world is everything that you observe in the world is very standard, right? It's a boring place. And it estimates the values of the parameters of a probability distribution such that they maximize the probability of the training data again. So do you mind shutting your laptop there? Yeah, thank you. So now here is the problem we're actually going to run into today and in the next class. And the problem is that sometimes the data provided may be incomplete. They may be insufficient to write out the complete probabilities. So in this case, you cannot estimate your model parameters directly using the data. And this could be because maybe the data themselves have missing components, or this could be because you know you're missing some information about how the data were produced. So let's take a look at the two cases. The first one, where the data themselves have missing components. If the data have missing components, here's an example. Let's say I'm trying to estimate a Gaussian distribution. We all just saw how to compute the probability, the parameters of a Gaussian. It's very easy. The parameters of the Gaussian are the mean and the variance. You just use the standard formula. The average of your training data is going to be your best estimate, your maximum likelihood estimate for the mean of the Gaussian. And the average of the outer products of the vectors is going to be your maximum likelihood estimate for the variance of the Gaussian. But then here's the problem. I'm giving you all of these data, but in each data instance, some components are missing. Now, this is a very common problem. It's incredibly common. Anytime you're doing, you go on, say, Netflix, and you watch a movie and it makes new recommendations, it's actually doing a maximum likelihood estimate, but in the process, it's actually learning a Gaussian distribution for all of the movie ratings assigned by various people. But then guess what? Nobody has watched 1 million movies, and there are 1 million movies out there. So each of you is providing a ratings vector where some movies are rated, but a large number of movies are just not rated. And so you're going to have incomplete data of this kind. Each of you has watched a different set of movies. So the vector of ratings is going to have missing components, and the missing components are going to be different for every single observation. And now you have to use these data to estimate the parameters of your Gaussian. How would you do it? Now, again, here is the problem. In the original problem, you want to estimate the Gaussian given a collection of data, but to estimate the Gaussian, you need the complete data vector in every single case. And so you would just be trying to find the mean and the variance that maximize the sum of the log Gaussians for all of the observations. But then many of our components are missing. So here, this is all the data you're observing, and these data are missing, right? And the problem is your maximum likelihood principle is only stating that whatever you have observed is commonplace. You cannot make any assumption about the things you have not observed, right? So the complete data you want is going to be the set of all the observed components and the unobserved components. But the only thing that you're allowed to maximize is the probability of what you have actually observed. So in this case, you would be trying to find the parameters of your Gaussian by maximizing this term here, where you're summing over all of the observation vectors. But in each observation vector, you're only observing some of the components. And so you're going to try to maximize the log of the probability of the components that you did observe. So who is 19? Yes. What would be the problem if I wanted to do this here? The Gaussian is, pardon me?
So because there are missing data, so the Gaussian will be calculated out in
Yes, absolutely, right? So you have the Gaussian that you have computed, defined, is on the complete vector. It's not defined on partial vectors. So its vector is defined on the union of the observed and the missing components. Whereas you're only allowed to use the probability of the components that you did observe. And so you are going to have to derive this from the probability of the complete data. And the way you would derive it is by marginalizing out the components that were missing, the ones that you couldn't observe. You'd be integrating out the missing components from the Gaussian. So the log probability of all of the data you did observe is going to have this horrible integral inside the log. And so this is the term that you would be maximizing. You're trying to maximize, you're trying to find the Gaussian mean and Gaussian variance that maximize this term here, the sum over all of the data, all of the observations, of the log of the probability of the observation, which in turn is obtained by integrating out, by marginalizing out the things that you did not observe in that particular instance. And the missing components are going to be different for each data vector, as we just saw. This is not a nice problem to be solving because you have a log of an integral. And I don't know about you, but if somebody gave me a log of an integral and asked me to maximize it, I'd go home. So this is bad, right? Now this was where the data themselves are incomplete. Let's look at another problem where there's something about the nature of the process that is missing. So let's consider a simple example, a Gaussian mixture model. Now, in many situations, the probability distribution of your data is going to have this ugly shape like this. It's, yeah.
Can I talk about this?
Yeah.
So I found a potential problem of this. It seems that if a missing
like if a data point has more missing components, it will have larger integration of probability.
You're going to be integrating over more components, yes.
Yes. So in an extreme case, if all the dimension data missing, the integration is 1.
So in that case, you haven't observed anything. It's not the log of whatever you observed is 0. So that's not going to contribute to your estimate at all.
Yeah, but if like most dimensions are missing, that probability is, I think, is overestimate.
You will have all kinds of problems depending on how much data is observed and how much data is missing. So you're right. You'll have all of those situations, but we are not addressing the statistical accuracy of the estimate itself. We're just saying that there is a problem right now, right? So here's the other case. I have a probability distribution of this kind, and it's ugly because it's got this multiple humped structure. But then in these situations, we like to model it as a mixture of Gaussians. So for example, if I have a probability distribution which looks like this, then I can say that this is the sum of this Gaussian plus this Gaussian plus this Gaussian and this Gaussian. So I can model this as a sum of a bunch of Gaussians. This is a Gaussian mixture model, and it's very popular, very common, because you can see that you can fit it to various kinds of distributions. The things you would have to do is that each Gaussian would have to be, a Gaussian by definition has a volume of 1. So you can't just add the Gaussians, you have to weight the Gaussians. And so each Gaussian is going to have a weighting factor. And so the actual Gaussian mixture model is going to look like this. You're summing over all the Gaussians of some P of k, which is the weight for the Gaussian times the Gaussian. And the weights themselves are going to sum to 1. That's the only way this whole thing is going to integrate to 1, because it's a probability distribution. But then the generative process behind a Gaussian mixture model is this. The model states that when you have a Gaussian mixture distribution, the actual generative process is a two-step process. In the first step, you're going to randomly select one of these Gaussians according to P of k. In the second step, you're going to draw an observation from the Gaussian. So it's a two-step process, and if you want to know how any individual observation was generated, you need to know all the details. Which Gaussian was it that this data was drawn from, and then of course the data observation itself. So in the ideal case, if I have a mixture of 3 Gaussians, red, green, and blue, how many of you are colorblind? It's a serious question, because I flashed this slide a few times, and I had some students who couldn't see that there were 3 Gaussians. There were 2 red Gaussians and a blue Gaussian. So anyway, so if you had this, then suppose I had a collection of observations, and I could tell you exactly which Gaussian each observation came from. So I told you that when I drew this vector, I selected the blue Gaussian and then got the data vector from it. When I generated this vector, I selected the red Gaussian and obtained the data vector from it. If this information were available, then estimating the Gaussians is trivial. All I have to do is to segregate all the blue vectors to the left, all the vectors that came from the red Gaussian, all the vectors that came from the green Gaussian, and then because I know all of these came from the blue Gaussian, I can just estimate the mean and variance of the blue Gaussian from these data, the mean and variance of the red Gaussian from this data, the mean and variance of the green Gaussian from the third data point. So this is easy. To be able to do this, the data I would need to know, what I would need to know is what the entire sequence of steps that the generating process followed in producing any given observation. The problem is that while we want this, we want the observation and the Gaussian for every data instance. What you're actually going to get is just the sequence of observations. You will not be informed which Gaussian every vector came from. And so you have the situation where once again you're only allowed to maximize the probability of whatever it is you have observed. That is what you're assuming is commonplace. And so you're going to have to find the mean and the variance, which maximize this term, the sum over all observations of the log of the probability of the observation itself. But then P of O is a mixture. It could have come from various Gaussians. So you really need to, you're basically saying the actual process chose a Gaussian and then generated a point from it. So the actual process generated both a k, which is the Gaussian index, and an O, which is the observation. But then if all you have is the observation, you have to integrate. You have to marginalize the Gaussian index out. And so that's this guy right here. P of k given O is the probability of choosing the Gaussian P of k times the probability of the specific observation, which is the second term. And this horrible term over here is what you're going to have to maximize. Again, the situation is that you have a summation, which is what you get when you're trying to marginalize out this category variable, which is the Gaussian index, inside the log. And once again, if you're asked to maximize something that has a summation inside a log and asked to do it directly, that's not a nice problem. And if somebody gives you the problem, they're not being nice to you, right? So this includes the log of a sum, which defies direct optimization. And so you need to have some alternate solution. Now, right after this, there are like 50 slides of math, which I'm going to spare you. But I expect you to sort of look over. And here is the general idea. The presence of missing data or variables requires them to be marginalized out of your probability. And when you do that, then if you have some parametric probability distribution, you end up with a term of this kind where you're trying to find the parameters which maximize the log probability of your data. But to compute the probability of any given observation, you're going to have to marginalize out whatever it was you did not see, the missing components within the data itself. And I'm actually explicitly introducing the semicolon theta over here to show you that it's a parametric model with parameters theta that you have to estimate. And maximizing this is trying to maximize the log of a sum or an integral which doesn't have a closed form in most cases. So we need something like gradient descent. You could just use gradient descent out here. Gradient descent would give you a reasonable solution. But we like to use something far more simple, so far more efficient, something called the expectation maximization algorithm. And so here is the trick we will use. We will try to get an approximation to this that is more tractable, something that doesn't have a summation within the log. And so the trick for this, at this point, I'll skip the math and I'll just try to explain this with figures. If you have theta as your variable, and this is summation x log of P of O, P of O will have to be marginalized over the hidden variables. Then this is the term that you're trying to maximize, and this is going to be some horrible function of this kind. And you're really trying to find the theta that which gives you the largest value for this. But it turns out that because this has this log of an integral or a log of a summation, finding a closed form solution is really hard. So here's what we will do. We will define some other function which is nicer, which is a lower bound on the function. And now you're going to maximize this lower bound. But it's very easy to come up with lower bounds. I can just say 0, right? Or minus infinity, that's a lower bound. That's not a useful thing to be maximizing. So ideally, you want the lower bound to be as tight as possible. So we define something called an auxiliary function. And the auxiliary function has an interesting property. The auxiliary function is guaranteed to be a lower bound on the log likelihood, but you will be allowed to make it touch the log likelihood function at a location of your choice. So for example, I would be able to say, out here, I want my auxiliary function to touch the actual log likelihood out here. If I do that, then the auxiliary function is going to end up looking something like this. Because it's a lower bound, it's always going to be below the main function, but I can touch it at some point. Once I can define an auxiliary function of this kind, then I get a very efficient hill climbing solution. And what is the solution? It's very simple. I'll start off with some initial estimate for theta. This is my theta 0. Then I'm going to construct my auxiliary function to touch my log likelihood at exactly theta 0. And then I will maximize the auxiliary function. If I maximize the auxiliary function, because it's a lower bound, then when I maximize the auxiliary function, I probably get out here, I know that this value is higher than this value, and this value in turn is lower than this value, correct? And so therefore, I know that at the new estimate, my log likelihood is higher than at the earlier estimate. Now I'm going to reconstruct my auxiliary function. I'm going to reconstruct my auxiliary function, but now this is going to touch it here. And so now the auxiliary function is touching my function log likelihood at the new location. I can maximize it again. So you can repeat this process. Eventually, the only time where the auxiliary function cannot be reconstructed and get a new maximum is where the auxiliary function itself touches your log likelihood right at the maximum. So this is the simple technique we will apply. And this kind of an auxiliary function is called an empirical lower bound, or an elbow function. So this is something you are going to encounter. If you ever do machine learning, it's very straightforward. The basic concept itself is very simple. How you derive it is something that it's not worth our time to actually go through. But here is what it looks like. This is going to be you want to maximize this guy. Instead of doing that, you define your auxiliary function, which has two parts. One is the a posteriori probability of the missing variables given the observations, and some parameter theta bar, and the other is the log likelihood of the joint probability of the missing and the observed variables. I won't again go through the math, but here is a guarantee. This guy is an auxiliary function. Theta bar is where it's touching. Theta is so this would be theta bar in this case. So this would be theta bar. That's where it's touching the actual function, and then you can maximize it with respect to theta, and then you can replace the maximum value with theta bar with the new maximum, and that gives you a very simple guaranteed non-decreasing algorithm for finding the maximum most likely theta. So this is all very nice. Math is great, right? Who doesn't love math? Does anybody not love math? How many understood this? You're lying, right? So I don't understand it. I went through this for many years. The math is all very fine. So the question is, what exactly are we doing? And that question, the answer to that lies in a slightly different place. Here's what I can do. Please don't run away. Okay, too bad. Okay. So suppose I have a bunch of data. Is it even there? Okay. Suppose I have a bunch of data, and I say these data are missing. But if I had those, I have a very easy way of estimating my probability distribution. And then if I were to ask you, okay, what do I do? Then if you want to be really, if you're not a mathematical genius, and you want to come up with an engineering solution who's 12, what would you do?
I would fake something.
Exactly. You'd fake the data, right? You'd plug something in. So I'm just going to complete the data by filling in the missing components. But then how do I complete the data? Can I put in any odd value? That won't make sense. You want to put something that's plausible. Okay. What do I mean by something plausible? Let me give you a totally random example. In this world, there are, at least on campus, people can largely be separated into, say, males and females. I'm not being politically correct over here. This is just an example, right? So these are males and females, right? And people can be tall and short. So there are four combinations of variables. And now I can say maybe this is tall people are like tall males are 0.6, no, 0.3, short females are 0.3, tall males are females are 0.2, short males are 0.2. Just some random numbers, right? This is the fraction of the population. And now if I give you a person and I told you this person is male, and then I ask you, is this person tall or short? What is your best guess going to be? Okay, how many of you think it's going to be a person's tall? Your best guess, right? Most of you. That's a number, right? But then let me just change that. And if I say, I can't really say if the person is tall or short, but I'm going to make 100 clones of this value. I'm saying there are 100 males in a room. So I'm just cloned this data 100 times and made 100 of them. How many of this 100 are going to be tall and how many are going to be short? 60 and 40, right? Straight from the number. So I would just say now I can begin filling in this missing value and say tall, tall, tall for 60%, actually. And then I can say short and short for 40%. And this is a plausible answer, right? This is what your statistics tell you. And so suppose I were to give you a large collection of men and women, then or even if then what you would do is assign short to maybe 60% of the women and tall to 40%, tall to 60% of the males and short to 40%. And then if I use this collection of data and re-estimated the probability distribution, will I get back the original table? What do you think? Right, obviously, right? Because I've constructed the data in terms of the probability distribution itself. These two are strictly equivalent. Everybody gets this? If I take this probability distribution and fill in the missing values in proportion for every observation that I get, then the filled in values are actually going to give me back the original distribution itself and vice versa. That's a stable situation, correct? But during the estimation process, here is what we are going to do. I'm going to sort of fake this distribution. Then from the fake distribution, I'm going to fill in the numbers over here. So observe that what happened here. In this example, I'm assuming men and women are both equally likely, correct? So this is clearly not going to work. But if in my observation I got only 3 men and 10 women, this distribution is fraudulent for my data, right? And I still want to get the complete table of probability distributions. So what would I do? I'm going to sort of start off with this assumption. Based on this assumption, I'm going to expand the males' heights for males and females this way. And then using this data, I can go back and re-estimate the table. And now the proportions of men and women are going to be more correct. But maybe this is going to jiggle the height probability distribution somehow. And then I can go back and forth, fill it up, complete my data, fill it up, and complete my data, right? So that's basically what we do over here. Here's a poll. Okay, 5 seconds, guys. All right. So the EM algorithm, as we just saw, is an iterative algorithm that can be used to estimate probability distributions when the data are incomplete. It iteratively maximizes an elbow function. It does not provide you a closed form formula. It's an iterative algorithm. Also, the elbow is a lower bound on the actual probability. It's also a function of model parameters. As we said, just saw, it's a function of theta. The other statement is not true. So so much for math. What does EM actually do? EM does what we were just talking about. Let's consider the first case where the data themselves are incomplete. So when the data are incomplete, you have all of these, you have this data, all the green components are observed, the black components are missing. So consider any one data vector. I'm going to fill in, I'm going to fake this data. I'm going to complete the data, right? And the way I'm going to complete the data is by making many copies of that data instance, because I don't want to make only one guess. Making just one guess is maybe not a very wise thing. As we saw in the male and female case, if I just guess tall for men and short for females, the actual probability estimate table that I'm going to get is going to be rubbish, right? I want to actually capture the proportions. So I'm going to make many copies, and then I'm going to fill this in, and I'm going to fill it in with every possible value that it can take. But any particular value is going to be filled in as many times, multiple times, and the number of times it's going to be used is going to be proportional to the probability of that value given the observations, right? Going back to my example over here, when I told you the person was male, why did you tell me 60% of these people were tall? Can anybody tell me? So who is number 5? So why did we say the person 60% were tall?
Because based on if they choose the man and the proportion of the 60.
Basically, this is the conditional probability distribution of height given that the person was male, right? So it is the conditional probability distribution of the missing data given the observed data. That's what we used for the proportions. So that's what we're going to do. We are going to use the conditional probability of M given O, and this is what we will use to fill in these values. So every one of these values is going to be filled in proportion to the value given O, the probability of the value given O. And so each one of your data vectors is now going to have many copies, a very large number of copies, and the missing values are going to be filled in, and the data vectors are being completed. And each specific value is going to be used in completion as many times as in the number of times each specific value is chosen is in proportion to the a posteriori probability of the data itself. Now, if the data are continuous valued, then how many possible, it's a Gaussian, right? So if it's a Gaussian, how many possible values will that missing component have, who is 13? How many possible values will it have? It's going to be infinite. It's going to be uncountably infinite, right? You can't really use this procedure. But it turns out that if you just work out through the math, you can think of this as the hypothetical this is the hypothetical thing that you're actually doing, but you don't need to explicitly do so. First, you can actually work out the math, and again, you need this a posteriori probability distribution. This comes from a previous estimate. Then you can use that, and then assume you can go back and ask, what would my mean and variance be if I had an infinite number of clones of every data instance, or not infinite, but a very large number of clones of each data instance, where every value for the missing component occurred in proportion to the posterior probability of that component. And then if you work out your arithmetic, there are lots of ugly equations over here. It turns out that you can actually get closed form solutions for the mean and the variance of the Gaussian. But of course, the proportions that you use depended on the a posteriori probability of the missing components given the observed components. And for that, you needed the complete distribution. So you're going to flip back and forth, exactly what we saw. That you'd start off with an initial guess for the table, fill this out, use these to go back and complete the table, and come back and forth. So it's an iterative algorithm, right? Mathematically, it's very clean. It's ugly, but conceptually, it's very clean. All you're really doing is filling out the stuff that you don't know in a reasonable manner. You do the same thing for Gaussian mixture. You're not actually given you're not told the actual Gaussian for each observation. So for each vector, you know that every Gaussian is theoretically capable of having generated that vector. So you're going to ask yourself, if I saw this vector 1,000 times, what fraction of times could it have come from the first Gaussian? What fraction of times could it have come from the second Gaussian? What fraction of times could it have come from the third Gaussian? And so you're going to clone that vector and distribute it, the clones, in proportion to the posterior probabilities of the Gaussians, once again, right? And then once you do that, so basically in proportion to the posterior probabilities of the Gaussians. And of course, to compute the posterior probability, you need the Gaussian parameters which came from the previous estimate of the model. And so here's what you do. Every vector is going to be cloned, and the clones are going to be assigned to the different Gaussians in proportion to the a posteriori probability of the Gaussian, just like we did for the male-female case. And then once you do that, you can segregate all the data out. You can go back to the original procedure. You pull out all the blue vectors, all the green vectors, all the red vectors. You can go back and estimate the parameters of your green, red, and blue Gaussians. Again, I'm not going through the math. The whole idea was to give you this concept that when you are missing data, what you really want to do is to fill in the data that you're missing. And you want to fill the data in a plausible manner. And what is plausible is a statistically plausible approach where the statistics are based on the current estimate of the distribution of the data. And then you go back and use the completed data to re-estimate your model parameters. And with the complete data, estimation is going to be easy. Right? This clear to everybody? Right. Now there's something really hideous out here that, if you have real valued data, then the number of ways in which you can complete any data vector is infinite, uncountably infinite. So you're sort of depending on the math being tractable, that you can somehow consider all infinite possibilities and somehow work out some math, and it will still give you a clean answer. This is not always going to be true. If that is not going to be true, then can someone who's sufficiently clever, that would be number 18. Who's 18? You're the one who's sufficiently clever. Can you give me an alternate solution? I still want to finish the data, complete the data. Maxwell? Thank you. I can always ask this guy. He's got an answer, right? So. Okay, so one of you guys, right? That's my answer corner. Anyway, here what I can do is, instead of considering every possible value in proportion to that posterior probability, it's sufficient to complete the data by sampling the posterior probability distribution. So over here, instead of saying that I'm going to be putting exactly 60% of them as tall and 40% as short, I can draw a random number, draw talls and shorts from a 0.6, 0.4 distribution and use those to fill in those values. That's easy over here, but in the case of the continuous value distribution, that's, sampling from a distribution is much simpler than working out the math of what would it be if I considered all infinite values. And then you can use the completed data to complete the missing components with the data by sampling possible values for these missing components from P of m given O, or in the case of the Gaussian mixture, P of k given O. And now that you have completed data, you can re-estimate your model parameters. So once again, this is just very straightforward. The point is, once you have complete data, it's very easy to estimate things. Right? So here is the overall EM principle for learning the distribution of a data, of a generative model. You're given data with some missing components. So you're going to initialize your model parameters somehow. Here you're going to initialize a Gaussian, maybe you may initialize a Gaussian mixture over here. Then you're going to iterate. You're going to complete the data by filling in the missing values according to the a posteriori probability distribution for the missing values. You could do this by sampling, or you could do this by explicitly considering every possible value. And then re-estimate the model from the completed data. And you iterate this process, and this should give you the correct answer, or a reasonably good estimate, right? Questions?
Why the process converge? So why this process give you a reasonable?
It's provably convergent. The provable convergence comes from the property that when you have the complete data, the estimate is a maximum likelihood estimate. So increasing the likelihood of the data. When you're sampling from the a posteriori probability distribution, you're choosing samples that increase the likelihood of the data again. So each step increases the likelihood of the data. So anyway. Okay.
People are watching online, I think.
Yeah, this is a toughie because there are four options to read, right? All right, let's stop. The first three options are right, the fourth one is wrong. So I won't read them out. Hopefully you've read the polls, right? And now I'm going to change topics. After having spent a lot of time talking about expectation maximization, yes? Yes. That's, there's so many solutions for that. Yes, it is an iterative algorithm. Like all iterative algorithms, it depends on the initial estimate. There is no guarantee that your final estimate will be good. Right? How many of you have heard of principal component analysis? Okay, most of you have heard of principal component analysis. Here's what principal component analysis does. You are finding, so who's 20, who's 4? Yeah, okay. What do you know of principal component? Have you heard of PCA? Okay, so you're out. Who is 7? Okay. What does principal component analysis do? You find something called a principal subspace, right? Here's what a principal component analysis does. You want to find a principal subspace such that when all vectors are approximated as some scaling, as some point on this principal subspace. In 2 dimensions, your principal subspace is just going to be a line. So you'd be approximating every vector as some scaling of the line. When you approximate it, you're going to make an approximation error, which is the length of the dotted line. And so you want to find the principal subspace that minimizes this total error, total squared error. And that one is going to give you your best lower dimensional guess approximation for the data. So the general idea is you're given some data and you want to find the principal subspace such that when you approximate every data point as its perpendicular drop onto the subspace, the total squared error is minimized. So what you would actually be doing is sort of searching through all possible subspaces until you find the subspace that actually minimizes the error, right? Now, those of you who actually are familiar with PCA will tell me that you're not really searching through all of this, that there's a closed form solution. And I want to assure you that I'm not ignorant of this fact. So just to impress on you that I'm not utterly ignorant, I have a couple of slides letting you know that I know that there's a solution for this, which is based on Argand decomposition. But then there's a different approach. And the different approach is this. When I try to here's what finding the business of the principal subspace really means. If you have any data vector x, then a subspace is fully characterized by the bases that compose the subspace. So what I mean is if I have a line, then this vector fully characterizes this line. Every point on the line is some scaling of this vector, right? If I have a plane in 3 dimensions, then maybe I have these 2 vectors which fully characterize the plane. Every point on the plane is going to be some linear combination of these 2 vectors. So these vectors which fully characterize the space are your bases. And so what we are trying to do over here is say it's maybe basis 1 W1 plus basis 2 W2. If I want to have a 2-dimensional representation, 2-dimensional subspace that I'm projecting the data on, then I'm going to again imagine that this is a 2-dimensional plane in 3-dimensional space. Then every point, these are my axes, I'm going to have my basis B1, I'm going to have the other basis B2, and any point can be thought of as some scaling of B1 plus some other scaling, in this case a negative scaling of B2, right? So I can write this as some B1 times W1 plus B2 times W2. Or I can put the vectors B1 and B2 into a matrix and the weights W1 and W2 into a vector, and I can just say x equals B1 B2 times W1 W2, right? If I have a collection of these guys, many such vectors, then each of these vectors can be written in the same manner. So I can have, extending this out, I can have x1, x2, this is my collection of vectors, is going to be the same set of bases, right? Because I'm trying to represent all of these vectors in this 2-dimensional space, but then the weights are going to be of this kind. W11, W12, this is for the first vector, this is for the second vector, and so on. I can just write this whole thing out in linear algebraic form. I'm not doing anything fancy, this is just linear algebraic, right? And so if I represent this as a matrix X, this as my, how have I written it? I've actually called this Z and I've called this W. So bear with my poor notation. Then I'm saying that the approximation of every data vector on the plane can be written, the approximation of all of my data vectors on the plane can be written as this form. X equals W times Z. These are my bases. These are the matrix of weights with which the bases can be combined to compose my data. So this is an approximation. And so I'm trying to find the bases and the coordinates of my data points in terms of these bases that minimize the total squared error. That's what finding the principal subspace really does. Now that's the math that all of us are familiar with. And now there's an iterative solution to this. The iterative solution is this. If I give you the bases, it's very easy to find out the coordinates for every data point, right? But then if you go back and look at it, this is symmetric in B and W. So if I give you W, it's easy to find B. If I give you B, it's easy to find W, right? So here is the approximation I can do. I can fix my W and find, or in this notation, I can fix my W, which are the bases, and find the coordinates for all the points. Then I can fix the coordinates for all the points and go back and find the basis W. And I can iterate through the process, and it's going to give me a solution, right? So when I do it that way, here's what happens. I have some data point. I'm trying to find the principal subspace on which the error is minimum. When I approximate every data point as being on this principal subspace, the error is minimized. So in my iterative solution, I'm going to assume that I know the subspace. I'm going to find the coordinates of all the data points on it. Then I'm going to fix my coordinates, and I'm going to find my W, right? So, and then this is going to give you my approximation of the data point at some point on the subspace. And I want to minimize the error between x and x hat. Let me redraw it linearly. If I redraw this linearly, then given the basis for my subspace, I can use the basis of my subspace to find the coordinates of my data points. Given the coordinates, I can find W to find the new data point, my best approximation of the data on the subspace, right? So I want to find W and Z such that the error between x and x hat is minimized. Is this looking familiar? What does it look like? That's an autoencoder, right? We saw this in the last class. This is just an autoencoder with linear activations. Now, there's a problem over here that when I'm trying to just do, the solution is not unique. And the solution is not unique because I'm saying x equals WZ. If I put W times some A, and then I wrote A inverse times Z, it gives me the same solution. So the solution is not unique. So if you want to get a unique solution, you impose some additional constraints. The constraints you're going to impose, one of the constraints we can impose is that the Z is really a large matrix of vectors. You can say that I want Z to have, the vectors in Z to have 0 mean and unit variance. It's just they're formed from a Gaussian. And that will give me a unique answer, a unique estimate for this for W. So again, this is just an autoencoder. I'm trying to find the W. And I could just do this by directly minimizing the error between the input and the output. But that solution is not unique. There are many different solutions, and they all represent the same subspace. If I want uniqueness further, I can impose some constraint in Z and say that Z must be unit mean, 0 mean and unit variance. But this is still just your regular autoencoder, right? So now, when I think of it procedurally, what am I really doing? I can fix my W and find my Z's, right? So I'm saying I'm going to start off with some initial guess. My statement is that if I knew the coordinates for every data vector, then I can find the basis for the subspace. So the data that are missing are the coordinates for every data vector. So if I had the Z for every data vector, I can find the subspace. Unfortunately, I don't have the Z. So I'm going to start off with some initial guess for the subspace, use that to fill in the coordinates for the data vectors, then use these coordinates to go back and estimate my subspace again, use the new subspace to find my coordinates, and repeat this process. And the whole thing is going to converge, right? Does this look familiar? What is this? Can everybody say that aloud? What was this? Say it aloud. Say it aloud, guys. Thank you, right? This is EM, right? So this was just EM. But then there's something missing over here. We just did principal component analysis, which is something that many of you are familiar with as some way of reducing the dimensionality of data. But then what I'm showing you is that principal component analysis can be computed using expectation maximization. Is going to give you the same answer. But then expectation maximization is a technique for learning generative models, right? What is the generative model out here that we are learning? So if you look at this, this is basically a linear autoencoder. I'm constraining z to have unit mean and 0 mean and unit variance so that I can get a unique answer. And so this guy here is the encoder, this guy is the decoder, right? And this decoder portion is in fact just a generative model. Basically what we are saying is that I can take any data, any z, I can pass where I can generate data from a standard Gaussian, and then I can pass my data from the standard Gaussian through a linear transform, and when that comes out I'm going to get data which looks somewhat like the data that I'm trying to represent. So the second portion is your decoder for the autoencoder. And so the generative story behind principal component analysis is this, that you have some data, you're trying to find the principal subspace for the data. That's basically what you're trying to do, right? And the generative story is that the data is being generated from a distribution, that you're first taking a Gaussian step from some central point on the plane, and then you're taking an orthogonal step at 90 degrees from the plane to get to your data. That's basically what the principal component analysis model is. So going back over here, when I was trying to find PCA, the PCA model says this. That, in the two-dimensional case, we had all of these points, and we said this is my principal subspace, remember? And the principal subspace is the subspace where the total squared error to all of these data points was minimized. That's how we defined it. So the generative model behind PCA is that I'm taking a step on this principal subspace, and the length of the step is distributed according to a Gaussian. And then once I get there, I am taking a step at 90 degrees to the principal subspace, and that's how I'm generating my data point. So basically the model says that I have taking a step on the subspace is the same as saying I'm taking a data point from a standard Gaussian and then multiplying it by the vector. The length of the step comes from a standard Gaussian. The vector tells me the direction. So I'm taking a z, I'm putting it through a times z. That gets me here to this point. And then to this one, I'm adding an error e, and that gives me x. That is the actual generative model that we've got behind principal component analysis. Is it making sense to you guys? Right? So this is what we're doing. That you're drawing your step size from some standard Gaussian. Then you're taking that step on the plane. And then once you get to the right point on the plane, you're adding some noise, which is also being drawn from a Gaussian. But this Gaussian has a very special property that the variance is always at 90 degrees, that the step is always at 90 degrees to the plane itself. Everybody clear? Right? So this is a generative model. I'm saying x equals az plus be, and my initial z is being drawn from a Gaussian. I'm transforming it through a. Then I'm drawing e from a Gaussian, and then I'm adding az plus e to generate x. So if e is Gaussian and z is Gaussian, then what is the distribution of x14? That will also be Gaussian, right? So the PCA model is basically assuming that the data are Gaussian, and the data have very specific parameters. Again, who is 24? Who's 24? Yes. What are the parameters of this model? It's right there on the screen. What are the parameters of this model? Okay, who's 1? Who's 1? Who was the first person in the class? Yes. What are the parameters of this model?
The mean, mu k and sigma k.
This model, that is your generative model, right? What are the parameters? Okay, I've obviously lost all of you, but I'll keep chugging on. I have to finish the class. Who's 10? What are the parameters? Yes?
0 mean would be variance.
The parameters are A and D. That's what are being used to generate the data, right? The Gaussian is being drawn from a 0 mean unit variance. Then you're multiplying it by A to get to the point on the plane. Then you're adding a noise, and the noise has a variance which is D. So in order to fully characterize the model, to characterize the distribution of the data that you get, look at the distribution of the Gaussian itself. The distribution of the Gaussian is going to be 0 mean, and the variance is going to be A transpose plus D. So those are the only two things that we need to know. So if you know A and you know D, then you know everything about the data. You can generate data from this distribution, right? So the parameters of this distribution are A and D. Principal component analysis implicitly obtains maximum likelihood estimates of A and D from the training data. That's what PCA is actually performing, right? For those of you who have encountered PCA, it's a maximum likelihood estimate. Now, if you think of this in terms of our autoencoder, then this was the decoder, right? The decoder had some weights matrix. If you had an autoencoder with linear activations, this was the decoder. And you are saying that the data that's going into this portion of the decoder, the entry to the decoder, is being drawn from a Gaussian. It's being transformed by this linear operation. And then finally, that's this term over here. You're adding some noise to get the final data, right? And to estimate the model itself, what do you need to do? To estimate the model, you need to know how to go from any given x to z. So basically, if I'm given a collection of data points and you're being told to estimate the model, then what you really need to know is to say where on this line was each data point, right? How much was the line stretched by for each data point? So the first step is, for every one of your training instances, you need to know z. And that's just a linear operation. So the encoder is finding the z for every one of your training instances. The decoder is transforming that again, right, back to the original data space. And you're trying to find this w and v to minimize the error between x and x hat. So this is just your standard autoencoder with the additional constraint that z must be standard Gaussian, right? So easy. This is just a autoencoder. And what kind of distribution does PCA actually represent? PCA represents distributions of this kind, where you say that the entire data have a distribution which lies very close to some subspace. So maybe, yeah, this is the subspace, right? You're saying that the entire data lies on some very close to some plane in the real world, but it has some fuzz off of the data. So the main component of the data, so you're saying that what you're observing is information on the plane plus noise orthogonal to the plane. So the principal component analysis model says that this guy here is your actual information data, x hat, and that it's being corrupted by some noise which is orthogonal to the plane, and that's how you get the full rank data. And so it assumes that your data are going to have distributions of this kind, that actually it's centered on 0, that the data is going to be almost close to some subspace. In 2 dimensions, it's almost close to a line. It's just got some fuzz around the line, right? So there's a poll, a final poll. We'll give them more than a minute. We need dust-free chalk. Okay, 5 seconds, guys. Here you go. So PCA finds the principal subspace such that approximating all training data by their projections on the subspace results in the lowest error. This was the first statement we made about PCA. An optimal autoencoder with linear activations reconstructs all data as their projections on the principal subspace. That's what we saw discussed even in the last class, that an autoencoder with linear activations is performing principal component analysis. It's finding the plane such that when every data point is approximated at some point on the plane, the total error is minimized. Now, we all just also saw that the bases with which you define the subspace are not unique, because given any plane, I can pick any 2 vectors on the plane and call them the bases. Now, one way to uniquely estimate the subspace is to require the bases of the subspace to be orthonormal. This is something that I haven't explained today, but that's part of the standard PCA technique that you actually learn anytime you learn PCA. But the other approach that we did see is to say that Z, the step size on the subplane, on the plane, the coordinates must be distributed according to a Gaussian. And these two are going to give you different sets of bases, but they're going to give you the same subspace. Anyway, yeah.
So these constraints give you 2 like families of potential bases. Is there any guarantee that like their intersection will give you one unique that satisfies both?
You're minimizing the error, so it doesn't matter, right? So think of it this way. This one, where was the chalk? Yeah, there's a chalk here. I'm minimizing x minus wz whole squared. If I think of wz as a unit, is the solution unique? It's a quadratic. Is the solution unique? I'm thinking of wz as the total wz as a unit. So if I think of this as, say, x hat, then it's unique in x hat, correct? It's just that within the x hat there are different answers. So you're always going to find the same subspace.
But if we want to impose both and like have some, like in addition to minimizing loss, if we wanted to impose,
it will not change anything. This loss is going to be minimized. All you're saying is that of all of these solutions, considering that this has the lowest error, of all of these solutions, I can impose those additional constraints without modifying the solution. You're going to find different sets. That's it. So anyway, yeah.
I was wondering how the solution would change if the dimensions of the data increase, because the number of principal components is usually the number of dimensions of the data. But here we talked only about the first principal subspace.
It's a principal, first principal component versus principal subspace. Principal subspace has many principal components, right? Okay. 2 dimensions, 3, whatever, right? Okay. Yeah. So anyway, just to close off, can I do something better? Now going back to this model of PCA that many of you should be familiar with, PCA assumes that the data lies on some space, and that anytime you generate data, you're assuming that the data are Gaussian, that anytime you generate data, you're randomly picking up a Gaussian data instance on the subspace, and then you're adding orthogonal noise to it. But then think about the real world. In the real world, if you look at an image of white noise, can you sometimes see images in it? If I randomly generate pixels, you will begin seeing patterns in it. You can see cats and dogs or what have you. You just look at the sky, you're going to see castles and people and dragons. If you just shut your eyes and listen to silence in a room, you can hear people whispering. That's where ghosts come from. So it's true, right? Noise has patterns. Noise is not orthogonal to your data. So the assumption that principal component analysis makes that the noise is always at 90 degrees to your data is fundamentally flawed. If you want to do something better than that, you want to say that this noise is no longer just required to be orthogonal to the data. It can be in any direction. It can even be just exactly like your data itself. And so the generative data, the simple extension that I would have to PCA is to say that I'm going to take a step, a Gaussian step on this plane, and then I'm going to add some noise to this Gaussian, to the point where the noise can be in any direction. The only assumption I'm making is that this being noise, the noise is uncorrelated. So that means this covariance matrix of the noise is a diagonal covariance matrix. That's the only assumption that I'm going to make. And this is a natural extension of principal component analysis that should actually give you a better characterization of the data itself. And so this is what we call the linear Gaussian model. It's called a linear Gaussian model because we are saying that the data goes through a linear transform. That's what defines your principal subspace. And then you have linear addition of Gaussian noise. So it's a linear Gaussian model, which says that to generate any data point, you're going to take some point step, Gaussian step on the plane, and then draw some noise and generate the data. But then because the step that you take off the plane is no longer required to be orthogonal to the plane, there are many different ways of generating any given data point, right? So we will continue with this example. So this is also called factor analysis. A is the loading matrix, Z are the factors, D is diagonal. We will continue with this, and this will take us to autoencoders in the next class. Basically, all autoencoders do, if you've understood principal component analysis, you've understood autoencoders. If you understood PCA and EM, all autoencoders do is to replace this A over here with a neural network. That's about it. Stop here. Thank you, guys.